So without further ado, it is my pleasure to introduce Heather Himmelberger. Heather is the director at the Southwest Environmental Finance Center at the University of New Mexico. Go ahead, Heather.
Good afternoon, everyone. Welcome to today's webinar, and I hope everyone had a great Thanksgiving. I know I enjoyed a few days at home with my family and my friends and had a great time, so I hope you all did the same. And welcome back to everybody who's been to either Webinar 1 or Webinar 2 or both. As a reminder, today's webinar is part of the Environmental Finance Center Networks project that we call Smart Management for Small Water Systems. We've received funding from EPA for this project, and it's allowed us to provide managerial and financial capacity assistance to small water systems all over the country. And in this context, we're defining a small water system as one that serves 10,000 people or fewer. Under this project, we've been able to provide a series of in-person workshops on asset management, rates and finance, energy efficiency, water loss, access to funding, and water system collaboration. And maybe some of you were able to attend some of those in-person trainings. As part of this project, we're also holding these webinars, and we're having webinars in most of the topic areas to accommodate anybody who wasn't able to attend an in-person training or maybe wanted to hear about a different topic than the one that they went to. Today's webinar is part of the Asset Management series of webinars. In this series, we are holding 5 webinars on asset management, and we're hoping that you can attend as many as possible, but each webinar is also completely standalone, so if you're not able to attend them all, that's okay too. And we recorded the last webinar, so if you've missed that one, that will be posted on our website soon. And then we'll be recording the rest of the webinar, so if you miss one, you can always pick up a webinar later on. So why do we want to do asset management at all? As a reminder, asset management is really a way to help you deal with the problems you're having with limited financial resources while at the same time having aging infrastructure and increasing regulations and increasing needs to meet level of service. So it's a systematic way to help you deal with those issues. And the good part about asset management in the methodology that we're teaching is it builds on what you already know about your system. And you already know quite a lot about your system between all the people that work there now or the people who've worked there in the past that you can tap into and all the other information you have. There's quite a bit that you already know. And we want to start from there. We don't want to start all over again from scratch. We want to start from where you're already at. It's also a very common sense approach, so it shouldn't feel very foreign to you. It should feel very natural, and you may even think to yourself, you know, I do a lot of these kinds of things already. And that's probably true. It's maybe just a different way to think about those things or a different way to package them up, different way to get information out of what you already do to make better decisions. It also helps you operate each asset in the most cost-efficient manner, and this is where we get into, you know, what should you do in terms of operation and maintenance with each asset? What do you want to do with repair, replacement, rehabilitation of all of your assets? It's also a way to try to change your operation from a very reactive operation, which is pretty common for most utilities, to a more proactive operation. So instead of reacting to every problem that occurs, every crisis that comes up, you can be much more planned and try to have your activities be preventative in nature rather than corrective in nature. And finally, a focus on understanding and managing risk. That's pretty much the essence of today's webinar, to talk about, you know, how do you understand the risk of your operation, the current operation? How do you manage that risk? There will always be some risk to an operation, and how do you decide how much risk is okay for your organization? There are 5 core components of asset management, which is again why we had 5 of these webinars. So the first component is current state of the assets, and in this component we're trying to take an inventory of all the physical stuff that makes up your system. And it's pretty hard to manage a system unless you know what it entails, and that's what we do in the current state of the assets. In level of service, we're looking at what do we want our assets to provide? What service level do we want to give our customers? What are we trying to achieve with the assets that we're managing? The third component, which is the focus of today's webinar, is criticality. Which assets are more critical to our sustained operation than others? The fourth component is life cycle costing. This is where we get into how are we going to operate and maintain our assets over time? How are we going to make those choices about repair, replacement, rehabilitation of our assets? And this is the focus of the next webinar. And finally, funding. In this component, we get into how much funding do we actually need over time, how much do we need now, how much are we going to need in the future to take care of our assets in both the operation and maintenance sense and the repair, replacement, rehabilitation sense. So how are we going to determine that amount of money? How are we going to gain support for getting the funding that we need for our facilities? So we'll just take a moment to recap what we covered our last two webinars. So first, the current state of the assets. I always think of the current state of the assets as the most straightforward part of asset management. And in this step, we look at what assets we own, where they're located, what condition they're in, how much life they have left, and what's their replacement value. So we're trying to inventory all the physical things that we have in our system and try to keep track of what the assets are. The second component is level of service, and this was the focus of webinar 2. And in this component, we talked about the fact that water utilities are really customer service businesses. That's the business that they're in. We manage assets in order to provide service. So we set goals to help us define how we want to operate the utility, what we want the utility to do, and then we want to be able to measure how we meet goals, whether we met the goals and how well we're doing. And I would call this step probably the most underappreciated component. A lot of people don't realize the value of setting goals and how that changes the way you think about your assets and how important it really is. The third component is criticality. And criticality, I would say, is sort of the heart and soul of asset management. And when you understand criticality and risk, you really get the essence of what we're trying to do with asset management. So the most important thing to think about when we talk about criticality is that not all of our assets in our system are equally important to us. Some are going to be way more important than others. So I have a couple of different pictures here, and the pictures on the left are assets that potentially could be more critical to your system. And this is very system specific. So your system may be very different, but here's the types of assets that might be critical. So for example, if you have a well and it's the only well serving your community, that could be very critical to you because if you lose that well, you're not going to be able to serve water. Similarly, if you have a storage tank and it's the only storage tank for your system, that may be a big problem for you. It would be a very critical asset because if you lost the storage tank, maybe you lose the ability to meet peak demands, maybe you lose fire flow, you might lose the ability to provide sufficient pressure to some of your households. So that could be a very critical asset to you. A pipeline that goes underneath a major highway could be a critical asset because if that asset failed, it might cause a lot of trouble on the highway. And finally, a pump. Suppose you only have one pump and that pump is necessary to supply your whole community. That pump could be very critical. On the other hand, if you have something like a cul-de-sac and a water line serving in a cul-de-sac with a few houses, that's going to be a lot less important to you because if that pipeline fails, there's a few customers are out of service, but it's a lot less than having a highway collapse or something like that. Or a gate valve. If you have many gate valves in your system and one particular gate valve fails, you just go a little bit further down the street and shut another one off. Hydrants, similarly, if you have a hydrant failure but you have hydrants spaced fairly regularly throughout your system, one individual hydrant failure may not be a problem. Or a meter, same kind of thing. Now again, I want to make it clear that it is very system specific. If you have very few hydrants in your system, having a hydrant failure may be actually very critical, so that might change your component from one side to the other. Or if you only have a few gate valves, that could be a much bigger problem. So again, it's just something to think about that in your given system, you're going to have a set of assets that are very critical to you and a set of assets that are less critical to you. So now we're going to listen to a video from Eric Saylor from Cincinnati, Ohio. And again, because we had trouble streaming the video portion, we're only going to listen to the audio portion. So Don, if you would, play the audio.
I think on the collection system side, we were, up until about 10 years ago, totally reactive, and when CMOM, that phase started coming into place, then we truly became more proactive. And then we were finding a lot of our problems, collapsed pipe and et cetera, that we didn't even know were there. But then where we needed to take the next step was implementing the asset management program then there was no prioritization of that proactive work. We were treating our major interceptors with just as much importance as an 8-inch sanitary line in a cul-de-sac. And if you're living on the 8-inch sanitary line in the cul-de-sac, that is the most important thing to you possibly. But as a whole, as managing a department and managing your assets, you have to treat those differently. And so one of the first things that we did on the collections side was, under the strategic plan, was to form that risk task team. And that risk team was set out, their mission was to help us develop that criticality of the assets. What are our priorities as far as our maintenance goes? To be proactive, but yet to be logical in the proactive nature. And then in turn to develop that probability of failure, so you can then in turn properly prioritize your capital investments.
Okay, so as was mentioned, what we want to think about when we're trying to figure out criticality is a couple of things. First, what is the likelihood that any given asset is going to fail? And second, what is the consequence if the asset does fail? So will an asset failure occur? And if so, how bad is that asset failure? And then if you think about it visually, you can look at a picture something like this, where we say probability of failure is increasing along one axis and consequence of failure is increasing along the other axis. And we end up with, say, 4 quadrants. And one, the high risk, which is in the upper right quadrant, are those assets that have a very high likelihood they will fail, and also a very high likelihood or high probability in terms of consequence that something bad is going to happen. If that particular asset fails, it'll be a bad thing. Down here in the lower left-hand box, these assets have a low probability of failure. In other words, it's highly unlikely that the asset will actually fail. And if it does, we don't really care. The consequence is low. In this box, we have assets that have a high probability of failure, but if they do, the consequence isn't all that high. And then finally, the last box are assets that probably are not going to fail, but the consequence could be really high if they do. So again, remember that this is system specific, but types of assets that might be in different boxes are fairly new pipe in residential streets would be fairly low risk because it's unlikely to fail, and if it does, it will only affect a few customers. Something in this box might be a very old piece of pipe in a residential area where, again, that pipe is probably likely to fail, but if it does, it's not going to cause a high consequence. Or maybe a valve in a system that has lots of valves. Maybe you have valves that are quite a bit older and they haven't been exercised, so maybe a particular valve might fail, but you just have to go down the street to turn another valve. An asset up here might be a fairly new water tank, but it's a water tank that serves the entire community, so the probability that that tank is going to fail is fairly low since it's new and in good condition and it's been maintained. But if it did fail, it would cause a major problem. And then we talked about a lot of the assets that could be high risk, like your an individual well, when it's the only one, or an individual pump, and maybe these are older, in poor condition. You know, you've had problems with them. So what you're thinking about is, if you had money to spend in your system, where are you going to spend it? So when you do a chart like this, you would want to put most of your time and energy into this high risk box and a lot less into the low risk box. And that's kind of why we do this. If you had all the money in the world to spend, you could just spend all you wanted on maintenance, operation, replacement, repairs, and you could pretty much spread it out throughout this entire chart. But we don't have that kind of money available, so we have to focus more of our effort, energy, money up into the high risk box and a lot less in the low risk box. So we want to really focus on these assets because if we can do something about the high risk assets, then the overall risk for our system will improve. So on the failure side, there's actually 4 different ways that assets can fail, and it's important to kind of remember all of these different ways. The first is mortality failures, and these are the most common kinds of failures that we think about, and usually when we think about asset failures, this is what comes in mind. And I have some pretty dramatic pictures there Mortality failure can also include things like leaks or stuck valves or anything like that. This is when something physical happens to the asset and it's failed because of a physical problem. A level of service failure is more related to a change in regulations, a change in customer demands or desires, something like that. So in this example, maybe you have a community that has 4-inch pipe right now. They decide that they want fire flow, and they're going to have to go up to 6-inch pipe to get it. So maybe the 4-inch pipe is in good shape, but you're going to have to replace it anyway to allow for fire flow. Or a well that maybe has arsenic in it. Prior to the arsenic standard changing, maybe it was fine, but after the standard reduced down to 10 parts per billion, the well was no longer able to be used. So even though the well might be producing water, and maybe a lot of water, it may be considered a failure because it no longer is able to meet the level of service, the regulatory requirements. So you may choose to take that out of service and get a well that has lower arsenic, and we would call that a level of service failure. You can have capacity failures. This is where the asset is not able to deliver as much flow as you want. So maybe the pipe size is too small and you need a bigger pipe size. Maybe you have some corrosion inside the pipe that's reducing the ability of the pipe to deliver water. So maybe the pipe itself is in decent shape, but it isn't able to deliver the capacity, or maybe a well isn't delivering enough water, or a pump, whatever the case may be, but you're not getting enough flow out of your asset. And finally, we have financial inefficiency. And this is where we're spending too much money to continue operation and maintenance, and it would be cheaper for us to replace the asset. Generally speaking, it's cheaper for us to maintain an asset than replace it, but there comes a point where that's no longer true. And I kind of doctored this picture up a little bit, but consider a piece of pipe that maybe you had to go back each time and clamp it again and again, and you'd see, you know, 6 different clamps there on a little piece of pipe, and you'd say, okay, well, that's probably at the point where we could have replaced that pipe rather than clamping it. Or maybe you have a pump that you're going back to repair over and over and over again. It would be cheaper for you to just get a new pump as opposed to continuing to repair it. So this is when we're getting into those cases where we're spending so much on operation and maintenance that it really isn't worth it to continue that. On the consequence side, we want to think about the triple bottom line. So triple bottom line contains 3 elements. One is financial, so we want to think about what are all the financial consequences that might occur. This is all of the cost to us of repairs or replacements or parts, overtime, fixing another asset. So for example, if the water pipe leaks and the pavement is affected above it, or you have to dig up the pavement to fix it, the costs that you have to pay to do that part should be included. It's really all the financial costs that go into the failure. Second is environmental. What are the environmental consequences that occur? Did water get discharged into a stream that contained chlorine, and now you had a problem with fish life? Or did you discharge water into a wetland and cause a problem? Or did you flood out maybe some endangered plants or something? So any kind of environmental consequence would be considered here. And finally, social. Social is all those impacts to your customers. Were they without water? Did they have inconveniences because businesses were shut down? Did they have to go around barricades? You know, what are all the effects to your actual customers, or did they lose confidence in you because of that? So when we think about consequences, we're trying to be holistic and think about all the consequences that occur, financial, environmental, and social. There are some ways we can reduce risk. If you think about the 4-box quadrant that we had before, and we had assets that are up in the highest risk box, there are some things we can do to try to move some of those assets out of that high risk box. One of the things is just by doing our routine and preventative maintenance. So as assets age, they may need more maintenance, and if we do that preventative and routine maintenance, that might help reduce the probability of failure of the assets, which will help reduce the risk. We can have redundancy. That's where we have 2 assets when we only need 1, for example, or maybe we have 3 assets where we need 2. So we're trying to put an extra asset in there so that if one fails, the other one can pick up the slack and do the job. And that way we can reduce our risk by reducing the consequences. The spare parts, keeping spare parts around can reduce how long the asset is out of service. So for example, if we have a pump that fails and we have spare parts for it that allow us to fix that pump very quickly, that can greatly reduce the consequence because we're able to put that asset back in service right away, as opposed to having to order spare parts and having to wait quite a while for the spare parts to come in. Specialized training in how to deal with different assets, how to take care of them, how to maintain them, how to monitor them, how to fix them could help. Replacing assets early is another way to reduce risk. If we have an asset that we just feel like we can't let it continue to be a risk to us, we can always replace it. And then finally, we can do some monitoring. We can monitor, say, vibrations of a pump, or we can put a camera inside a pipe, or we could monitor the thickness of a metallic pipe. Things like that. We can do leak detection. So we can do different types of monitoring to sort of check how our assets are doing. And that can help us put in place some of these other things like preventative maintenance or replacing early to help us reduce our risk. So when we calculate criticality, there's three basic factors that go into it. We look at the probability of failure, the consequence of failure, and our redundancy factor. And then we say our criticality is really our probability of failure times our consequence of failure times our redundancy factor. And the redundancy factor is going to reduce the criticality because it's going to be something less than 1 if there is any redundancy in the system. So how might we address or assess criticality? There's all kinds of tools that can be used, from very, very simple to very, very complex. So the simplest tools would be something like a very basic ranking of all of your assets to say, okay, from a 1 to 5 scale, we're going to say what the probability of failure is for each asset on a 1 to 5 scale and what the consequence of failure is on a 1 to 5 scale. Then we'll do an assessment of redundancy, and we'll multiply that out. That would be a very, very simple criticality analysis. Going up to the higher end, we'll start looking at factors that affect failures, factors that affect consequences. We'll give, many factors, maybe rank each asset on a 1 to 100 or a 0 to 100 scale and see how they rank. So there can be some very sophisticated ranking systems, again, down to very simple ranking systems. And you can always start with a lower level ranking system and build up to something more advanced later on. So you can start simply and then build up. I'm going to show you just a couple of, or just an example of how it can be applied in a fairly simple case. And we'll just take one asset class. So when I talk about an asset class, I mean a wells or pumps or tanks. We're talking about one specific kind of asset. So for this example, we're saying we've developed some factors for probability of failure, and we're saying that several things go into how likely it is that a particular well might fail. So for example, the age is one factor, clogging history, regulatory water quality, which is more of a level of service concern, aesthetic water quality, which again is a level of service, and depth of well. And in this particular example, we're saying that they're having more trouble with shallower wells than deeper wells. Again, these are very system-specific issues. This is not, something universal. You would pick your own factors and your own criteria for how you would rank things. And then we can apply those factors to each of the wells. We're saying this particular community has 5 wells, and so each one is ranked according to those factors. And we've done a very simple across-the-board ranking where we're saying that each of these factors has the same weighting. You may decide that past clogging problems is the most important factor as in terms of whether or not the well has failed. So you might want to make that twice as many points. Or you might say that regulatory water quality is most important. So in this example, we've left it all equal, but you can change that and you can give weighting to different factors. So then we do the same thing for consequence of failure. And in this example, we've done things like look at the number of people served, the cost to replace the well, number of critical customers served, time to repair. And we've said those would rank 1 to 5. So again, we applied even weighting to all of those factors, and we come up with a score, a total score for the consequence of failure. Then we want to look at redundancy. And I've just developed some of my own rankings for what I want different redundancies to be. So if there's no redundancy, it's a 1, meaning that we're not going to reduce the risk at all. And then you can apply pretty much whatever scores you think are the best way to do it in terms of different types of redundancy. The one thing to remember, though, is the score for 100% or higher redundancy never goes to 0. Because no matter how much redundancy you have in your system, you can never guarantee that a redundant asset is going to perform, because the same condition that might have caused the first failure may cause all the assets to fail. And there's plenty of examples of that, you know, in non-water settings where, you know, the Fukushima plant over in Japan had a triple redundancy for its electrical power, but all 3 of those power sources failed. We had, you know, the plane that went down in the Hudson River, both of the, it had redundant engines, but both engines were affected by the same problem. So again, we never want to give it a 0, but it can be a pretty low score if it's 100 or higher redundancy. So then we'll apply redundancy factors to our wells, and here are the factors. So in sum, we can take the probability of failure score times our consequence of failure score times our redundancy factor to come up with a total score, which are these factors here. And you can see based on this, the south side well has the lowest score and the central well has the highest score. And if you look at it visually, it will look something like this, putting it on our high risk box. So we have 2 wells that come out in the high risk, we have 2 wells that come out in moderate risk, and 1 well that's in the low risk box. So that just helps us sort of visualize what's going on. So again, if we were trying to decide where to spend our maintenance dollars and our time in terms of doing maintenance on a well, where would we go? Well, we would want to do the work in the central well and the west side well, because those are our highest criticality wells. So if we were choosing, you know, where to put some effort, that's where we would put it. When we get our data done, you know, in either the tabular form or some kind of visual, one thing you want to do is ask yourself the question, does it make sense to you? Does it seem to portray the data well? Does it seem like everything makes sense? If it does not, you might want to go back to the analysis and say, do you think that we should weight certain factors? Should we have given more weight to, say, clogging of the well or age of the well, rather than leaving each factor equal weighted? Did we put enough consequences in there? Did we miss a consequence? Did we not consider something? And then do the analysis again if it doesn't seem to make sense. You don't want to just go willy-nilly and say, hey, I thought this well should have been the highest, I'm going to change it. You really want to go back to the analysis and say, you know, does the analysis itself make sense, and change the analysis, not the results. You also want to ask yourself the question, do I carry too much risk, not enough risk? Is it just about the right amount of risk? I mean, anytime you have a utility, there's always going to be some risk. You can't ever take that to 0. But you want to say to yourself, does it seem like, you know, we're really high risk operation, or, you know, does it seem okay? So again, you know, what if the data looked more like this? What if we had the 5 wells and 4 of them were very high risk, high criticality wells? How would that change how you view the data? Would you think differently about it and say, well, maybe there's a problem here? You know, we have 5 wells, 4 of them are very high risk, and 1 of them is moderate risk. And, you know, if this was the only water source for the entire community, you might be quite concerned about it looking like this. If you had surface water sources that were taking over for the wells, maybe it's not as big a deal. But you'd really want to look at this situation and say, is this too much risk for me to be carrying? Should I do something about it? What if it looked like this? What does that tell you? It could tell you a couple of things. It might tell you that you have very new assets. Maybe the wells are fairly new, they were just put in, and so there really isn't much probability of failure, and you have 5 of them and maybe you only need 2 or 3 of them operating at the same time, so there's a lot of redundancy, so there's not very high consequences. So if you saw something like this, it might tell you that, or it might tell you that you're spending an awful lot of money to work on your wells and get the risk down, and maybe some other asset in your system needs the resources and the time. So if you saw something like this, you would want to think about, am I spending too much money on my wells at the expense of something else? Then you might want to ask yourself, is there anything you could do to reduce risk? If you have a high risk or a moderate risk situation, what could you actually do that would help you reduce the risk? So some of those things that we mentioned before about monitoring, or having spare parts, or getting extra training, or replacing an asset early, are any of those available to you to reduce the risk? And then if you wanted to take on those strategies, what's the best way to get support for that? How you get your governing body and your public to want to support that? Because typically it's going to mean resources. You're going to have money or people resources in order to reduce the risk. So how are you going to get that? The best way is to really explain the risk properly to the governing body. I mean, it's always up to the governing body how they want to spend their money and what choices they want to make, but you have to do your best to explain the risk situation. And if you have the hard data behind it, where you can say these are the factors that we use to determine the probability and consequence of failure, it's a lot harder for somebody to attack that rather than just going in and saying, hey, we got a problem here, the wells are too high risk. Once you have the information that really stands to stand behind, you can really explain that risk to your governing bodies and to the public, and hopefully get the support that you need to go forward with getting the resources to reduce the risk. It's important to remember that criticality changes. It's not static. Every day is going to change a little bit because you're using up your assets every day that they're in operation. We need to reassess criticality at least every year. Sometimes we might want to do it sooner, but at least every year we want to go back and look at these factors and say, has anything changed? Has anything changed with the wells? Did we do some major maintenance items that reduced the probability of failure? Or did something change where we have critical customers that are now being served? A new business moved in and they said if we don't supply them with water, we get fined or something. That might change a consequence. You also want to reassess your criticality when you make major changes. So if you're doing major upgrades to your facility, replacements, construction, that type of thing, you really want to go back and assess again your criticality, because it's going to change a lot when you've done these big projects. So you kind of want to see, what's different about it now. We're now going to watch a video that talks about criticality for the Albuquerque-Bernalillo County Water Utility Authority for their steel water lines. So this again is looking at criticality in terms of one specific asset class, and they're reducing it to just the steel water lines, so a very specific asset class. So Don, if you will, start the audio.
This map shows steel line criticality, which is the probability of failure and the consequence of failure. Those two combined creates the criticality, or the risk for steel water lines. And so we looked at, in terms of probability of failure, the number of water leaks. So this shows some of the areas that we've looked at in terms of probability of failure and consequence of failure. The likelihood that a line is going to break again. You can see our scale between 1 leak, between 2 and 4 leaks, between 5 and 13 leaks, and then between 14 and 22 leaks. And this is per line segment. And then another component is the line size, if it's not meeting fire flow protection, or if it's a major transmission line and could cause a major leak. So these are the different types of probability of failure. The consequence includes railroad crossing, if it's in a high traffic or moderate traffic corridor or arterial, proximity to schools or hospitals, and if it's located in a tourist or business center. So these are the components of the probability and consequence of failure that will lead to the total risk or criticality of still water lines.
And you might ask yourself, why did they want to specifically focus in on steel line criticality? And one of the reasons in this particular utility they were having a lot of trouble with steel water lines, which make up only about 5% of their system in terms of total pipe, were having about 50% of the overall water breaks. So they could tell that most of the problems were occurring in one specific type of pipe. However, they didn't have enough money to replace all the pipe at once, so they had to be very selective in terms of what pipe they were going to replace. So if you can only invest a little bit of money and do a little bit of replacement at a time, you really have to figure out which pieces are the most critical to get out first, because you don't want to be doing the best pieces first and then you have to leave the rest of the pieces in for a long time. You want to do the worst pieces first. So they were going about criticality analysis to try to figure out which of their steel pipe was in the worst shape, so that they could replace that specific pipe, they could reduce their risk. And in a short time after doing this, within like a couple of years, it dropped from 50% of the breaks being on steel to 35%, so that they knew that they were having an impact on the overall steel issue. So it can be a very powerful tool that can be applied in this asset class kind of way, or it can be applied across the whole utility, looking at how do wells compare to tanks, compare to pipe, etc. So to finish up our webinar today, we'll talk about taking it to your facility and what you might be able to do in your own water utility. And we've had this on a couple times before, and we'll continue to keep it up. The first thing you might want to think about is developing a team of people at your utility that might be able to help you with asset management. So this could include as many or as few as you have available to you. So if you're a smaller utility, just a couple of people. If you're a larger utility, probably a larger group. And it would include finance, operations, management, all of the people that you can gather together who have good information about your system. The second thing is completing the interactive asset management IQ tool that's available on the web, either as a downloadable PDF that you can just do on paper, or interactively that you can do on the computer. And this helps you to establish a baseline. Where do you stand right now in terms of your asset management practice? So it kind of gives you those tools to think about, you know, where am I now? And so when you start implementing asset management, and you can take the IQ again later, maybe 6 months to a year from now, you can start to measure how much better your practice has become. So the first thing that you can do after today's webinar in terms of criticality is maybe pick a class of assets to try a criticality ranking. So you saw an example that I showed you today for wells. You also heard an example from Albuquerque on steel water lines. Just pick maybe a class or even a subclass of assets and say, okay, I'm going to try a criticality ranking on this particular subset of assets. So it could be wells or pumps or tanks or whatever you choose to pick. You know, just pick some one class of assets that you think you might be able to try a criticality ranking on. And if you want to pick one that doesn't have very many assets, that's fine too, because you're just trying to try out the tool and try out the thinking. So if you only have maybe 3 pumps and you want to try it on that, that might be a good way to get your feet wet and get started in it without it seeming too overwhelming. Then choose a set of criteria for probability of failure for that class. So when you looked at the example that I showed you, I had picked things like clogging of the well, whether it was meeting regulatory guidelines, that type of thing. So choose different factors that you think would be good ways to estimate how that particular asset might fail, and think about all the potential modes of failure, not just mortality, but level of service, capacity, financial inefficiency. So you can include things like how much money I'm spending on operation and maintenance, things like that. So think about a set of criteria for the probability of failure, and then do the same thing for the consequence of failure. And then again, you can think about assets or consequences that are all three: financial, environmental, or social. You can put different criteria for each of those types of consequences. And then try to come up with your ranking. Do you want it to be a 1 to 5, 1 to 10? How do you want each of those criteria ranked? And what would it mean if you're a 1? Give it a specific, such as I showed you before. If it was a population-based, I gave different population ranks and said 1 was this population and 2 was that one. So come up with some ranking criteria for each of your probability and consequence factors. And then you want to determine if there's any redundancy for that particular class of assets. Sometimes there is and sometimes there isn't. If there isn't, you can skip the redundancy part. If there is, think about how you want to define redundancy. So if it's no redundancy, it would be a 1. And then think about what factor you want to apply if it's 50% redundant or 75% or 25% or 10%. What kind of factor do you want to have for your redundancy? And then finally, apply your POF and COF factors, your probability of failure and consequence failures, to your assets in the class and determine your risk. So once you've gotten your probability, consequence, and redundancy, do the calculations like we were showing today and determine what is the risk for each asset in that class. And then try to come up with a visual representation of your data. What would the data look like in a picture form? And it doesn't have to be the 4-box quadrant that we have. It could be something else. It's whatever you think would visually display that data so that somebody can see the risk of one asset versus another, and can kind of see, how bad one situation might be, if there's one asset that's worse off than the others. So what we've talked about today is really looking at a particular class of asset. You can eventually combine those classes together and say, okay, well, how does the highest risk pump compare to the highest risk tank or compare to the highest risk pipe, and that type of thing, so that eventually that's where you want to go with criticality, where you're looking at an overall big picture of your system and saying, okay, I have different criticalities for pumps and tanks and wells and pipe and valves and hydrants, and how do they sort of all combine together? And so that after you would do individual classes, you can kind of think about how you might want to compare one to another. If you choose that each ranking that you do is a 1 to 100 scale, then you could maybe compare each to each other that way. You can choose other ways of doing it, but we wanted to focus today just on having you think about your, say, an individual class of assets. How would you do a criticality analysis on just that one individual class, so you can kind of get a feel for what the process is like, and then you can apply it to the rest of your assets. And then think about what the data tells you. Do you think it makes sense to you? Does it tell you that you have too much risk, not enough risk, about right? What is that data telling you? Is it telling you that you should be taking some action to reduce risk? And if so, what action might you take? So we want to thank EPA again for providing funding for this project. We really appreciate the opportunity to be able to come to you and give you some information about asset management. And we have our contact information up there, Dawn and myself. If you have questions after the webinar, you're welcome to contact us. And then we have about 10 minutes left, and we're going to open it up. If anybody had questions, you were free to type them in during the session, or if you have a question now, please feel free to type your question in, and we'll answer as many as we can until the time runs out. So Dawn, do we have any questions today?
We do. The first one, if you can go back up a few slides to the Asset Management IQ link. Someone asked for that, and that way it'll just be on their screen instead of me trying to read it to them. Thank you. And then we have a question from Judy. She says, as a regulator, most of my operators would say they already know their system and they don't need to go through this exercise. They just know because of their system experience and knowledge. So then what is the benefit of them spending the time to go through this process?
Well, I would say that sometimes people say that, but it's not really true. And I can give a very specific example of this. We went and worked with a small utility a few years back, and we asked them some of these basic questions about, what their thoughts were on criticality and which assets were most critical to them. And they told us that their water meters were the most critical asset. And they said that they needed to replace their assets, their water meters, with radio read meters, and they felt that that was the most important thing for them to do. And we started asking them some more questions about why they felt that way. And they said, well, part of it was the heat in the summer. It was very hot for the operators to go out there. It took a lot of time, in their opinion. It was kind of a very, much a pain in the behind kind of thing to do. And they really wanted radio read meters because they thought they could get the data more accurately and more consistently if they did that. So none of that is incorrect information. I'm sure it was a pain for them to go out and read them. It was cold in the winter and warm in the summer. And it would be nice to have radio read meters. The problem was when we actually dug into their assets and started working with them on an asset inventory and then a criticality analysis, it turns out that they had 2 wells, each one served by 1 pump. And about half the community was served by 1 well and pump, the other half served by the other well and pump, and there wasn't a lot of redundancy between the 2 parts of the community. And it turned out one of the pumps was already almost in failure mode. It was very poor condition. It was not operating well. They were having a lot of problems with it. They didn't think it was going to last them much longer. And they hadn't really done anything to address that particular pump failure. They weren't prepared to replace it. They didn't have spare parts on hand. They had no plan of what they were actually going to do. So they were ready to spend money on radio read meters when they had a pump that was going to fail, and if it did, was going to take out, half the community of water. So sometimes people get a little bit off in terms of what they think is actually the highest criticality of the system, and so I think it's not always accurate to say that they definitely know which pieces are the most important. They knew that that pump was failing, so that part of the knowledge was in their heads, but they were off in terms of how that ranked compared to the consequence of failure of the water meters, or the need to replace one versus the other. And the other example I would give you is the steel line situation with the example that we showed in Albuquerque. They knew that that was a problem. I mean, steel lines were a major problem, and that was known. The problem was that they didn't know which individual pieces of pipe to replace. That was not as obvious. It was much more difficult to say, okay, if I can only replace 1 or 2 miles of pipe a year, which is about the level they've been able to do, it ranges probably between 1 and 3 miles of pipe a year, you have to be very selective out of the 85 miles that they had, which 1 mile would you actually choose, or which 2 miles would you actually choose. And the analysis comes in to really help you maybe focus in on, well, where should I put my 1 or 2 mile replacement, because all 85 miles is not the same. Even though I know that's a critical asset for me and is causing lots of problems, I don't know which individual piece it is. So I would suggest that while they have some great information available to start with and to work from, it really is important to have the fundamental analysis behind it so that you actually have the backup to say, this is why we have the risk that we have. So I think it is a really important step, and it isn't, just wasting their time to go through this.
And Bridget made a comment which we absolutely agree with, and it kind of goes right into the wording in the question. The operators just know it, and that's exactly right. It's in their head what happens when they leave, or when they retire, or if something happens to them. You lose all of that knowledge with that person. So thank you, Bridget, for that comment. We have run into that before, too, where an operator moves from one state to another and took the filing cabinet with him. And all of that information went with him, not just head knowledge, but paper knowledge. So it's very important to go through the process.